Welcome, Axor, Galactic Observatory. Tonight, the journey begins with two small spacecraft that left Earth in 1977 and never came back. Built with less power than a household light bulb and less memory than the simplest modern device. Voyager 1 and Voyager 2 crossed the giant planets, uncovered volcanoes on distant moons, revealed hidden oceans beneath their ice, and became the first human-made objects to enter interstellar space. What they found beyond the familiar edges of the solar system was far stranger, more beautiful, and more unsettling than anyone expected. In this documentary, the story moves slowly through that immense darkness, following the path of the Voyagers from the outer planets to the silent space between the stars. If this kind of deep space journey fascinates you, please like the video, subscribe to Axor, Galactic Observatory, and stay with us as the mission drifts farther into the unknown. Far beyond the familiar planets, beyond the last broad sweep of Neptune's orbit, and beyond the scattered belt of icy bodies that circle in the deep cold, two small spacecraft continue moving outward through a region that for most of human history had no practical meaning at all. This is not empty space in the simple sense. It is thin, structured, and active, but active on scales so faint and slow that it resists ordinary imagination. Voyager 1 and Voyager 2 travel through this darkness as the most distant artifact ever made by human hands. They move through a medium where sunlight still exists, but arrives weak and narrow, no longer warming metal in any familiar way. At that distance, the sun is reduced to an unusually bright star, still dominant, still central by origin, yet no longer able to define the environment in full. The spacecraft drift through a borderland where the outward breath of the sun weakens and the matter between the stars begins to assert itself more clearly. This outer region is shaped by the heliosphere, a vast bubble created by the solar wind, which is the steady flow of charged particles released by the sun. For a very long distance, that outward flow pushes against the thin gas of the galaxy and creates a cavity in interstellar space. Inside that bubble, conditions are still influenced mainly by the sun. Outside it, the wider Milky Way becomes the stronger presence. Voyager 1 has crossed that boundary. Voyager 2 has crossed it as well, by a different path and in a different year, confirming that the border is not a neat shell with a uniform shape, but a shifting surface shaped by solar activity, magnetic pressure, and the changing properties of the surrounding galaxy. The region beyond the heliosphere is called interstellar space, though the phrase can sound more dramatic than the reality. It does not mean the spacecraft have reached another star. The nearest star system remains tens of thousands of years away at their present speed. It means instead that they now travel through matter that does not come mainly from the sun. The plasma, which is a gas so energetic that atoms are broken into charged particles, has a different character there. The magnetic field behaves differently. Cosmic rays, which are high-energy particles moving through the galaxy, grow more intense once the protective influence of the heliosphere falls behind. The crossing was not marked by a gate or line in the dark. It was recognized through measurements. Instruments on Voyager detected the drop in solar particles, the rise in galactic cosmic rays, and the change in plasma behavior that together revealed a genuine transition. The result is one of the strangest achievements in the history of exploration. Human beings reached interstellar space not with vast ships, not with living crews, not with powerful machines built in the digital age, but with two compact probes launched in the 1970s, still following the momentum given to them decades ago. Around them there are no landscapes, no horizons, and no visible roads. There is only a gradual change in density, pressure, radiation, and magnetic structure. Yet this sparse region matters because it is the place where the sun stops being a local ruler and becomes instead one star among many. The heliosphere itself had long been understood in theory, But theory could only describe it indirectly from within. Voyager made it measurable from the edge. It revealed that the boundary is shaped by motion and pressure rather than by perfect symmetry. It showed that the solar system, when viewed at its outermost influence, is not a set of isolated planetary orbits fading into nothing, but a moving interaction between the Sun and the galaxy through which it travels. The Sun carries its magnetic field outward with the solar wind, and that field bends, twists, and weakens across immense distances. Eventually it meets the interstellar magnetic field, and the encounter produces a frontier that is neither fixed nor simple. The spacecraft now sample that frontier from beyond, sending back traces of a region no earlier civilization could even have named with precision. The scale involved remains difficult to hold in mind. Radio signals, travelling at the speed of light, take many hours to move one way between Earth and the Voyagers. A command sent from Earth enters space, crosses the orbits of the planets, passes through regions once visited in person by the spacecraft long ago, and only then reaches its target. A reply returns on the same long path, faint and delayed. This means that every exchange is a conversation with the past. This spacecraft are never contacted in the present tense of ordinary life. They are always where they were many hours ago, and Earth is for them where it was many hours before that. Distance has stretched communication into a slow, physical fact. Even so, the link persists. That persistence gives this outer darkness a strange intimacy. It is unimaginably far, yet still in contact. The space beyond the heliosphere is also a record of larger events in the galaxy. Interstellar plasma and magnetic fields carry traces of stellar winds, ancient explosions, and the slow circulation of matter through the Milky Way. The Voyagers are not equipped to explain all of this in complete detail, but they can register enough to show that the region between stars is not silent in a scientific sense. It is full of motion at very low density, full of particles accelerated by distant processes, full of structure that only becomes visible through patient measurement. In that sense, the emptiness is not empty at all. It is only far beyond the scales that human senses evolved to notice. The two probes continue outward through this cold medium, with no expectation of arrival. They are not headed toward a destination that will be reached in any human age. Their present role is simpler and more profound. They report from a place where the local environment of the Sun gives way to the broader conditions of the galaxy. They mark the outer extent of direct human measurement. They show that exploration can continue after the original map is complete and after the original mission has ended, because the boundary itself becomes a subject of knowledge. In this way, the first fact of their present situation is not only distance, it is transition. Voyager travels in the long twilight between the solar neighbourhood and the true interstellar dark, carrying the last active touch of Earth into a region that had once existed only as an abstraction. The two spacecraft that now move through interstellar space are remarkable not because they are large or powerful, but because they are small, limited, and still alive long after their designers expected silence. Each Voyager is about the size of a compact automobile, with a central body wrapped in insulation, a large dish antenna aimed back toward Earth, a long boom carrying sensitive instruments away from the body, and a framework of arms and appendages arranged not for beauty but for function. Their appearance reflects an era when every gram mattered and every part had to justify its presence. They were built for a mission measured originally in only a few years, yet they continue after nearly half a century, surviving not through abundance but through careful design, redundancy, and the gradual sacrifice of everything not essential to communication and core science. At the centre of their endurance is power. The Voyagers do not use solar panels because sunlight becomes too weak in the outer solar system for panels of practical size to support a scientific mission. Instead, they rely on radioisotope thermoelectric generators, devices that turn heat released by the decay of plutonium into electricity. This source of power is steady, but it is not endless. Each year, the available electrical output declines a little more as the fuel decays and the system ages. That decline shapes every decision made by mission engineers. Instruments are turned off one by one. Heaters are reduced where possible. Subsystems are evaluated not for convenience, but for whether they are still worth the precious watts they consume. The spacecraft are alive in the engineering sense, yet they live in a condition of managed scarcity. Every remaining measurement now depends on choices made far from the spacecraft, by teams who must decide how to stretch a fading energy supply across as many remaining years as possible. Their memory and computing power belong unmistakably to the early 1970s. Each craft carries only about 69 kilobytes of onboard memory. By modern standards, this is vanishingly small. It is less than the memory required to hold a low-resolution photograph on an ordinary present-day device. Yet the spacecraft use that small capacity with discipline. Their computer systems are divided among specialized functions, including command handling, attitude control, and data formatting. They do not compute in the modern sense of large flexible software environments. They perform narrow tasks, carefully defined and robustly maintained. Their data recorders, based on magnetic tape technology, reflect the same era. Their processors operate at speeds so modest that comparison with ordinary household electronics can seem almost absurd, and yet none of this prevents them from doing what matters most. They can keep track of orientation, collect instrument readings, package data, and send that data back across billions of miles to Earth. Their transmitter is also modest in power, only a few tens of watts, weaker than many simple household light sources. By the time the signal reaches Earth, it is unbelievably faint. It arrives at the great antennas of the deep space network as a whisper buried in noise, so weak that extracting it requires extraordinary sensitivity, careful error correction, and patient accumulation. That this works at all is one of the quiet marvels of modern engineering. The spacecraft do not shout across space. They murmur, and Earth listens with instruments large enough and precise enough to hear. Survival has depended not only on original design but on adaptation. The spacecraft were built with backup systems for crucial functions, because the engineers understood from the beginning that no repair mission would ever be possible. If a major failure occurred in deep space, the mission would depend entirely on whatever alternatives had been included at launch. Over the years, those backups became the difference between continued operation and final loss. One of the most famous examples came when Voyager 1's primary attitude control thrusters, which keep the antenna pointed accurately at Earth, began to degrade. Engineers revived a backup set of thrusters that had not been used for decades. These dormant components, preserved in the cold of deep space since a distant earlier phase of the mission, responded successfully when called upon again. It was an event that seemed almost improbable even to those who understood the system best. The same history contains jams, glitches, resets, memory problems, and strange behaviors that demanded creative response from Earth. In every case, the delays of distance made the process more severe. A decision on Earth could not be tested quickly. A command took hours to arrive. The result had to wait hours more. Diagnosis therefore required patience, unlike anything in ordinary engineering. The spacecraft became machines operated through time lag and uncertainty, where every action resembled careful surgery performed by correspondence. Another challenge is institutional memory. The Voyagers were built in a technological world that no longer exists in full. Some of the programming languages, hardware practices, and testing procedures belong to an earlier generation. Many of the people who designed the systems retired long ago. Some have died. Documentation exists, but paper records and aging technical materials cannot fully replace experience. Over time, NASA and the Jet Propulsion Laboratory have had to preserve not only the spacecraft, but also the human knowledge needed to communicate with them. In some cases, retired engineers have returned to help current teams interpret old systems or forgotten operational logic. This means the mission depends on two kinds of endurance at once: the endurance of machines in cold space and the endurance of expertise on Earth. Each depends on maintenance. Each weakens if neglected. Each represents continuity across decades. The spacecraft also endure physically in an environment that punishes materials slowly and without pause. Radiation damages electronics. Extreme cold alters the behavior of lubricants, seals, and structures. Micrometeoroid impacts remain possible, even if rare. Thermal cycles in earlier phases of the mission place stress on components never expected to serve for so long. The scan platforms that once pointed cameras and other instruments suffered problems. Many systems that defined the spectacular planetary encounters are now inactive. The cameras themselves were turned off years ago because the probes no longer pass worlds to photograph, and because power must be reserved for more relevant instruments. In this late era, the Voyagers are stripped down to essentials. They no longer function as full planetary observatories. They function as survivors. This reduction gives them a certain stark clarity. Their present purpose is not broad exploration in the old sense, but persistence at the edge of reach. Their remaining instruments sample plasma, energetic particles, cosmic rays, and magnetic fields. Their antenna returns those measurements in a data stream so thin and delayed that every bit resembles a recovered fragment from a vanishing source. The machines now seem almost biological in their condition. They are old, resource-limited, selectively impaired, still responsive, and cared for from afar by people who know that decline is inevitable, but not yet complete. In that sense, the Voyagers reveal something larger than technical skill. They show how much can be achieved by building cautiously, by preparing for failure before it arrives, and by accepting that longevity comes less from perfection than from resilience. Their greatness lies not in power or complexity, but in the disciplined refusal to stop working. In the summer of 1977, the outer planets are arranged in a pattern that does not occur on any ordinary human schedule. Jupiter, Saturn, Uranus, and Neptune occupy positions that allow a spacecraft launched at the right moment to move from one giant world to the next by borrowing energy from each encounter. The opportunity is not a corridor in space and not a fixed road, but a temporary harmony of motion. Each planet travels in its own orbit with its own period, and only rarely do these separate cycles line up in a way that makes a chained passage outward possible. For mission planners, this alignment is not merely convenient, it is transformational. Without it, visiting multiple outer planets would require a level of propulsion, mass, and expense far greater than the technology and budget of the time could easily support. With it, one carefully launched spacecraft can fall past one massive world, gain speed from that planet's motion around the Sun, and be redirected toward the next. In principle, the entire outer solar system becomes reachable through celestial mechanics rather than brute force. The mathematics of this possibility had been understood for years before launch. What made the moment urgent was that the geometry would not remain favourable for long. The window lasted only a few years. After that, the planets would continue on, the arrangement would dissolve, and the next comparable opportunity would not return for generations. The people preparing the mission understood that they were working inside a brief interval offered by the solar system itself. The planets had to be treated not just as destinations, but as moving partners in a sequence that could not be improvised later. This gives the launch year its real meaning. 1977 is not only a date on a calendar, It is the moment when a rare dynamic structure exists across billions of miles, and human engineering is ready just in time to use it. The idea that would later become Voyager begins in an even more ambitious form. Mission designers imagine a grand tour, a coordinated exploration of the 4 giant planets made possible by the unusual alignment. The concept carries the excitement of a once-in-a-lifetime scientific chance. It promises comparative study across the major outer worlds, opening the possibility of understanding not one giant planet in isolation, but an entire class of worlds, their moons, atmospheres, rings, magnetic fields, and internal differences. In a deeper sense, it also promises a new map of the solar system, replacing the distant blurred view from Earth-based telescopes with direct encounter and measurement. Yet such ambition meets the usual realities of politics and funding. Space exploration depends not only on orbital mechanics and scientific desire, but on budgets, priorities, public mood, and the larger history in which national agencies operate. The late 1960s and early 1970s are not an unlimited age of expansion. The era of Apollo has already demonstrated what concentrated national effort can do, but it has also established a scale of expense that policymakers are reluctant to sustain indefinitely. The outer planet mission is therefore shaped from the beginning by subtraction. What science wants in full is not what government is willing to fund in full. The original Grand Tour is cut back. What survives is leaner, narrower, and more cautious. 2 spacecraft are approved rather than a larger and more elaborate program. Their official primary mission is limited to Jupiter and Saturn. Anything beyond that is treated as contingent, dependent on spacecraft health, navigation success, and the availability of further support. This narrowing of the mission might seem at first like a reduction of vision, but it also creates the conditions for a different kind of success. By forcing restraint, it produces spacecraft small enough, light enough, and practical enough to be built and launched within the available framework. The modest official goals do not erase the larger possibility. They preserve it in latent form. If the first encounters go well, if the engineering holds, if the timing remains exact, then the road outward can continue. The alignment itself provides the chance. The spacecraft only need to remain alive long enough to take it. In this sense, the outward journey begins before launch, inside a tension between what is planned openly and what is hoped for quietly. Engineers and scientists know that every decision must serve immediate requirements, while also leaving room for extension. Trajectories are selected not only for the first target, but for what may become possible afterward. The timing of launch, the mass budget, the instrument suite, and the spacecraft durability are all shaped by this logic of preserving future options. Even the choice to launch 2 spacecraft matters here. They are not redundant in the simple sense of one backup for the other. They follow different trajectories and schedules, allowing the mission as a whole to cover more possibilities and hedge against failure. If one craft is lost, some science may still survive. If both succeed, their combined paths can reveal far more than a single probe ever could. The launch dates reflect this precision. Voyager 2 leaves first on the 20th of August, 1977. Voyager 1 follows on the 5th of September, taking a faster path that will allow it to reach Jupiter and Saturn sooner despite launching later. The numbering preserves the order of intended encounter priority rather than launch sequence. From the beginning, the mission therefore already contains a subtle reversal, an indication that chronology alone does not govern meaning. What matters is not who leaves first, but who reaches the crucial targets on the needed timetable. The alignment of the planets turns that timetable into the central fact of the mission. Every correction and every maneuver serve a structure that human beings did not create. The planets are in motion regardless of human hopes. The launch succeeds only because calculation and hardware are matched. For a short time, to the deeper clockwork of the solar system. That match gives the mission a character different from many earlier space efforts. It is not simply a direct thrust toward a nearby objective. It is an insertion into a moving pattern spread across the outer system. A missed launch period, a navigation error, or a failed encounter would not merely delay arrival. It could break the chain entirely. The later destinations depend on the earlier ones. Saturn depends on Jupiter. Uranus depends on Saturn. Neptune depends on Uranus. The opportunity is therefore cumulative and fragile. It resembles a line of falling dominoes stretched across the solar system, except that here the falling is controlled and the timing must be exact over years rather than seconds. Seen in this way, the summer of 1977 is one of those rare moments when celestial conditions and human preparedness overlap. The planets offer a passage. Human beings recognize it, calculate it, and commit 2 machines to it. Everything that follows begins with that brief permission granted by orbital geometry, a permission that had been forming for centuries before anyone could use it, and that would not come again for generations. Before Voyager becomes the longest-reaching mission in the history of space exploration, it exists as a compromise. That fact matters because compromise shapes not only what the spacecraft can do, but also what kind of story the mission becomes. The original concept for the outer planets had been grand in the strictest sense. Scientists and mission designers see the rare alignment of the giant planets and understand that it could support a sweeping expedition across Jupiter, Saturn, Uranus, and Neptune. The phrase Grand Tour captures both the scientific richness of the idea and the confidence of the period in which it emerges. The outer solar system appears, for a brief time, as a connected domain that could be crossed by design rather than by isolated effort. Such a mission would allow comparative study of the giant planets as a family of worlds. It would create a broad portrait of their atmospheres, magnetic fields, moons, rings, and internal differences. It would turn a series of distant points of light into places with structure and history. Yet for all its scientific elegance, the Grand Tour collides with financial and political limits that are as real as any physical law. Large space missions are never decided by science alone. They are funded through institutions that must weigh cost against many competing demands, and the outer planets do not enjoy the immediate symbolic urgency that had once surrounded lunar exploration. The public imagination is still shaped by the triumph of landing on the moon, but that triumph has also shown the price of very large programs. In the years after Apollo, national priorities shift, enthusiasm remains, but it is tempered by caution. The outer planets are distant, the mission duration is long, and the return appears uncertain to those who do not live inside scientific planning. Congress looks at the projected expense of the full program and recoils. The result is cancellation not of the opportunity itself, but of its most ambitious form. The mission that survives is reduced in scale, narrowed in official scope, and built under stricter constraints. This reduced mission becomes Voyager. The official plan is modest by comparison with the dream that preceded it. 2 spacecraft are approved, not as components of a fully funded 4-planet campaign, but as a more practical pair aimed first at Jupiter and Saturn. 4 years of operation are expected. Uranus and Neptune are not guaranteed destinations. They remain possibilities that depend on excellent performance, continued political support, and the continued survival of the spacecraft themselves. This redefinition could have diminished the mission permanently. Instead, it has the opposite effect. The reduction forces discipline. It produces machines that are lighter, cheaper, and more tightly focused. The total cost of the Voyager program, while still substantial, is far below what a fully realized Grand Tour would have demanded. Over time, this economy becomes one of the mission's most striking features. The spacecraft that go on to transform planetary science and then continue into interstellar space are not the products of unlimited investment. They are the products of constraints shaped intelligently. In historical terms, this matters because it reminds us that exploration does not always advance by choosing the largest possible design. Sometimes it advances by preserving enough of the original vision inside a form that institutions are willing to support. The reduction from Grand Tour to Voyager is therefore not simply a story of loss, it is a story of salvage. NASA and its partner institutions do not obtain everything they want, but they protect the essential possibility. They keep the launch window alive. They build spacecraft durable enough to exploit it. They retain a scientific instrument package rich enough to justify the risk. They choose trajectories that preserve options beyond the official minimum. What is cut away is scale, not intelligence. What remains is enough. That word acquires enormous weight in the Voyager story. Enough funding to build and launch, enough instruments to produce transformative science, enough redundancy to survive the unexpected, enough flexibility to continue outward if the first encounters succeed, enough institutional patience to treat success not as a fixed endpoint but as something expandable. The program is lean, yet not brittle. This balance becomes visible in the way the spacecraft are presented publicly and managed internally. Outwardly, the mission has clear defined goals. It will visit Jupiter and Saturn. It will return unprecedented data. It will do so within a credible budget. Internally, there is a wider awareness that the spacecraft may achieve much more. Their paths are not random. Voyager 1 is placed on a trajectory optimized to reach Titan, the largest moon of Saturn, whose thick atmosphere already makes it one of the most intriguing objects in the outer solar system. That choice means Voyager 1 will be deflected out of the ecliptic plane after Saturn and will not continue on to Uranus and Neptune. Voyager 2, by contrast, follows a route that preserves the possibility of further planetary encounters if Saturn is passed successfully and if the spacecraft remains healthy. The mission is therefore already divided between immediate certainty and future chance. One spacecraft is assigned a critical scientific goal at Saturn. The other carries the possibility of continuing the reduced Grand Tour by practical means. This arrangement shows how deeply the legacy of the original vision remains embedded in the supposedly smaller mission. The ghost of the Grand Tour survives within Voyager's design choices. The political context also gives the mission a different public character, because Voyager is not sold as an extravagant all-at-once conquest of the outer solar system. It can grow in stature through performance rather than through promise alone. Each success earns the next stage. Jupiter justifies Saturn. Saturn justifies Uranus. Uranus justifies Neptune. Decades later, the surviving spacecraft justify continued interstellar operations. This incremental pattern may lack the dramatic simplicity of a single vast commitment, but it creates a rare form of credibility. The mission does not demand belief in all its future triumphs from the beginning. It proves itself repeatedly. That process makes the eventual scale of its achievement even more striking. A program once defined officially as a 4-year mission to 2 planets becomes a 5-decade exploration reaching beyond the heliosphere. The contrast between the modest approved baseline and the actual historical outcome is so extreme that it reshapes the meaning of prudent design. Voyager becomes evidence that conservative planning can coexist with extraordinary results. The mission's reduced origins also deepen its symbolic value. Had the full Grand Tour been funded at once, its success would still have been great, but it would have represented the execution of a maximum ambition. Voyager instead represents something more subtle. It shows what happens when a civilization nearly loses a rare opportunity, preserves a smaller version of it, and then discovers that the smaller version contains unsuspected endurance. It is a story in which limitation does not extinguish wonder. It compresses wonder into a more survivable form. By the time the spacecraft leaves Saturn behind, the reduced mission has already outgrown the assumptions that created it. By the time Voyager 2 reaches Uranus and Neptune, the original cancellation has been answered not by complaint, but by achievement. The Grand Tour had been cut back by human institutions. The planets themselves remain where they are. The smaller mission, once launched, finds a way to meet them anyway. The spacecraft that leave Earth in 1977 are not designed as monuments. They are designed as tools, and every visible feature reflects that purpose. Their structure is practical, angular, and sparse. A large high-gain antenna dominates the form because communication over immense distance is one of the central requirements from the beginning. Behind and around it sits the bus, the main body containing electronics, computers, fuel lines, and control systems. Long booms extend outward to separate delicate scientific instruments from electrical noise and magnetic interference generated by the spacecraft itself. The arrangement makes each Voyager look slightly improvised, as if assembled from necessities rather than imagined as a single elegant object. That impression is accurate. The design is an answer to constraints imposed by mass, power, radiation, temperature, and the impossibility of repair. Everything must work in deep space without maintenance, in an era before modern miniaturization, under conditions that can damage electronics, freeze materials, or cause small failures to grow into permanent loss. The official expectation of a relatively short mission does not reduce the seriousness of these demands. If anything, it sharpens them. A 4-year journey to Jupiter and Saturn still requires that every component survive launch, cruise, planetary encounter, radiation exposure, and long-range communication with very little margin for intervention. The result is a spacecraft philosophy built on simplicity where possible, redundancy where necessary, and careful specialization throughout. Each Voyager carries 10 main scientific instruments. Together they are meant to see, measure, detect, and characterize the environments of the giant planets and their moons. The imaging system provides photographs across different filters and resolutions, allowing scientists to study cloud patterns, surfaces, ring structures, and evolving atmospheric phenomena. Spectrometers analyze light and energy at wavelengths beyond ordinary vision, revealing composition and temperature. Magnetometers measure magnetic fields and their changes across space. Plasma instruments sample the charged particles that flow from the Sun and surround planets. Cosmic ray detectors register high-energy particles from solar and galactic sources. Plasma wave antennas listen for electromagnetic activity in the surrounding medium. Photopolarimeter systems and other devices extend the mission's ability to study rings, aerosols, and atmospheric scattering. Each instrument has its own requirements for pointing, power, thermal conditions, and data handling. The spacecraft must therefore function as an integrated platform where scientific capability depends on a stable body, reliable orientation, and a communication system able to compress enormous distance into a usable trickle of information. None of this is easy with the technology of the time. The onboard computers are not general machines in the modern sense. They are separate, purpose-driven systems, each responsible for defined tasks such as executing commands, controlling attitude, or formatting engineering and science data. Their memory is tiny by later standards, and their flexibility is narrow. Yet their narrowness is part of their strength. They are designed to do only what the mission requires, and to do it reliably. Data storage also reflects the era. A digital tape recorder allows the spacecraft to capture observations when immediate transmission is not possible, and then send them later. This capability matters during fast planetary encounters, when instruments may generate more information than can be sent to Earth in real time. The recorder becomes a buffer between fleeting events and the slow link home. Without it, much of the close encounter science would be lost. The designers also know that any critical system without a backup becomes a possible single point of failure. Redundancy is therefore built into major functions, especially those involving command, communication, power regulation, and attitude control. This does not mean every part is duplicated. Mass limits forbid that. It means the most mission-critical elements have alternative paths or spare components where feasible. The logic is harsh but clear. Once the spacecraft leave Earth, there will be no servicing mission and no physical rescue. If a vital component fails and no alternative exists, the mission ends. Redundancy is thus a form of time bought in advance, added at launch to be spent years later if trouble appears. This conservative engineering style is one of the reasons the spacecraft endure so long. The thermal design is equally important. Deep space is not cold in the simple everyday sense. It is thermally unforgiving because objects receive intense sunlight when close to the inner solar system, very little when far away, and cannot rely on surrounding air to carry heat where it is needed. The spacecraft must therefore keep instruments and electronics within operating temperature ranges using insulation, heaters, surface coatings, and careful internal layout. Too much heat in the wrong place can damage systems. Too little can cause lubricants, materials, or electronics to behave unpredictably. The large planets add more challenges. Jupiter especially surrounds itself with intense radiation that can upset circuits and degrade components. Shielding is added where necessary, but shielding increases mass, and mass competes with fuel and instrument capability. Every protective choice carries a cost. The same is true of propulsion. The Voyagers do not carry powerful engines for dramatic maneuvers. They carry small thrusters for orientation and trajectory corrections. These are enough for the mission because the spacecraft rely mainly on launch energy and planetary gravity assists rather than sustained propulsion. Still, those small thrusters become critical. They keep the antenna pointed toward Earth. They orient instruments during encounters. They allow the spacecraft to maintain stability over decades. A failure here could leave a spacecraft alive but mute, unable to direct its narrow radio beam home. The mechanical systems that point instruments also matter. The scan platform can move cameras and detectors with precision during planetary flybys, allowing the spacecraft body and antenna to remain properly oriented while science instruments track targets. This capability greatly improves the quality of observations, but it also adds mechanical complexity. Over time, such complexity becomes vulnerability. The fact that engineers later find workarounds for scan platform problems speaks not only to operational skill, but to the reality that the spacecraft are intricate enough to face aging in very specific ways. Even the external appearance of the Voyagers tells this story of function under constraint. The long magnetometer boom keeps magnetic measurements away from interference. The radioisotope generators are mounted on extended supports to separate their heat and radiation from the central body. The antenna must remain dominant because communication is the mission's lifeline. The whole machine is a balance of competing demands held together by careful planning. It is not beautiful in the ornamental sense, but it possesses the severe beauty of something made honestly for a difficult task. The official expectation remains modest at launch. 4 years, Jupiter and Saturn, perhaps more if conditions allow. Yet the spacecraft are built as though modest goals do not excuse fragile design. They must be ready for long cruise periods, intense planetary environments, and failure modes no one can fully predict. In that readiness lies the deeper character of Voyager. The probes are not machines of excess. They are machines of preparedness. Their lasting achievement begins not with the discoveries they make, but with the engineering discipline that allows them to survive long enough to make them. Bolted to the side of each spacecraft is an object that serves no navigational function, no mechanical necessity, and no immediate scientific role in the ordinary sense. It does not help the probe survive radiation, measure plasma, or point its antenna toward Earth. Yet it has become one of the most widely remembered parts of the Voyager mission, because it carries a different kind of purpose. This object is the Golden Record, a 12-inch gold-plated copper disc enclosed in a protective aluminum cover and launched into deep space with each spacecraft. It is at once physical artifact, cultural selection, scientific diagram, and symbolic gesture. Its existence rests on a simple recognition. The Voyagers may continue moving through the galaxy for periods far longer than any human institution, language, or nation is likely to endure. Long after their power is gone and their instruments have fallen silent, the spacecraft themselves may persist, drifting through interstellar darkness for millions or even hundreds of millions of years. If they are to carry anything beyond hardware, it must be something compact, durable, and comprehensible in principle to a finder that does not share human language or history. The result is not a message in the narrow sense of a greeting sent with expectation of reply. It is more like a condensed self-portrait of a species placed in a bottle and released into a cosmic ocean that offers almost no chance of discovery. The physical design reflects this long view. Gold resists corrosion and remains stable in vacuum. The record is protected by a cover that includes symbolic instructions for playback. Those instructions begin from scientific constants rather than from cultural assumptions. They refer to the hyperfine transition of neutral hydrogen, a physical process that can serve as a universal reference unit for time and frequency. They include a pulsar map showing the position of the Sun relative to 14 pulsars, each identified by a characteristic period, allowing a capable interpreter to locate the spacecraft's point of origin within the Milky Way. They also show how the analog signals on the record can be turned into images. These markings are not decorative. They are an attempt to begin communication at the level of shared physics, assuming that any intelligence able to recover the record would know mathematics, atomic structure, and astronomical measurement. From there, the contents unfold into a portrait of Earth and of human life. The selection process is guided by a committee chaired by Carl Sagan, whose understanding of planetary science is matched by a strong sense that the record should represent not only technical accomplishment, but something broader and more humane. The images encoded on the disk include scientific material such as mathematical definitions, the structure of DNA, the chemistry of the atmosphere, and the arrangement of the solar system. They also include pictures of human anatomy, reproduction, birth, children, adults, food, architecture, landscapes, animals, insects, plants, and daily activities. The intent is not to produce a complete encyclopedia of Earth, which would be impossible, but to suggest the range of a living world. The images place the human species within a larger biological and planetary context. They do not present only machines, governments, or achievements. They present bodies, environments, and relations. A newborn child, a hand, a horizon, a field, a city, a wave, a vertebrate skeleton, a diagram of continental drift. These become pieces of a single effort to say what kind of world produced the spacecraft. After the images come the sounds and voices. Greetings are included in many languages, ancient and modern, broad in scope even if necessarily incomplete. Some are formal, some are simple. Their brevity becomes part of their force. A few seconds of language must stand in for cultures that developed over millennia. The record also contains sounds of Earth itself, including wind, rain, surf, thunder, birds, whales, footsteps, heartbeat, laughter, tools, engines, and other acoustic traces of a living planet. These are not merely samples of noise. They are evidence that Earth is not a silent place, and that human life unfolds inside a wider chorus of water, weather, organisms, and motion. Music follows, selected from different traditions and historical periods. Western classical works appear beside music from Asia, Africa, and the Americas. A single species that divides itself in countless ways tries, within severe limits of time and format, to send a statement that it contains multiplicity. The result cannot escape the biases of those who chose it, yet it still reaches toward a principle larger than taste. The record suggests that intelligence is not only analytical, it is also rhythmic, emotional, ceremonial, and aesthetic. One of the most intimate inclusions is less widely known. The record carries a compressed representation of the brainwaves of Andruyan, recorded while she reflected on love, history, and the human condition. In a strict technical sense, it is data. In another sense, it's a private inner state turned into a transmissible pattern and placed among the official emblems of Earth. This quiet addition changes the emotional texture of the entire object. The record is not only a scientific and cultural archive, it is also touched by personal feeling. The species that launches it does not send only formulas and maps, it sends traces of attachment and inward life. Yet the scientific honesty underlying the project never disappears. Those involved understand perfectly well that the chance of any other civilization ever finding either spacecraft is extraordinarily small. The Voyagers are not directed toward nearby stars. The distances between stellar systems are so vast that a probe can wander for immense stretches of time without approaching anything. The record is therefore not based on practical expectation. Its meaning lies elsewhere. It is a declaration made despite improbability. It says that a technological species facing an indifferent universe can still choose to describe itself in terms wider than utility. It can choose to send evidence of thought, sound, and beauty. In that sense, the Golden Record is also a mirror. It reveals what the makers believe is worth preserving when space is limited and the audience may never exist. The answer is not merely science. Though science is central, it is a combination of knowledge, environment, culture, and care. The record travels outward attached to machines built for planetary encounters. Yet it points beyond those encounters toward a more durable question. What does a civilization think it is, when given one small disk and one unrepeatable chance to speak beyond itself? Voyager carries one answer, not complete and not final, but sincere in its reach. The journey from Earth to Jupiter is not a straight act of approach, but a carefully arranged fall, one in which motion, timing, and gravity are used together with extraordinary precision. After launch, the spacecraft do not race outward under continuous thrust. Their rockets provide the initial escape from Earth. But what follows depends far more on celestial mechanics than on onboard power. Jupiter, the largest planet in the solar system, becomes not only a destination but a machine of motion. Its immense mass bends the path of anything passing nearby, and if the geometry is chosen correctly, a spacecraft can borrow a small part of the planet's orbital energy around the Sun. This borrowed energy changes the spacecraft's speed and direction, without requiring it to burn large amounts of fuel. The principle is often described as a gravitational slingshot, though the actual process is subtler than any familiar sling. The spacecraft falls into Jupiter's gravity well, accelerates as it approaches, swings around the planet along a precisely chosen curve, and then departs on a new path that carries it outward far faster than it could have managed through launch energy alone. The success of this maneuver depends on exact navigation, because Jupiter is not merely large. It is large in a way that magnifies error. A trajectory aimed slightly wrong at enormous distance can become unusable by the time the spacecraft arrives. This means that the approach to Jupiter begins, in a practical sense, long before the planet appears large in the cameras. It begins in calculations performed on Earth, in tracking data measured across millions of miles, and in the small correction burns that gradually refine the path. The spacecraft carry only limited propulsion, so these corrections must be modest and efficient. They are not opportunities to recover from major mistakes. They are adjustments to preserve a delicately chosen geometry. The target is not simply Jupiter as a whole, but a specific passage through space near Jupiter, at a specific time, at a specific angle, with specific consequences for the route beyond. The gravitational assist is therefore a test of planning stretched across interplanetary distance. Voyager 1 reaches Jupiter first in March of 1979, about 18 months after launch. Voyager 2 follows later that same year. The order matters because the earlier arrival begins the scientific return sooner, but the underlying significance is broader. Both spacecraft have now completed the first great transfer of the mission. They have moved from the inner solar system, where planetary exploration had already become familiar through earlier missions, into a regime where distance, delay, radiation, and navigation all grow more severe. Jupiter marks a threshold not only of size but of mission logic. If the encounter succeeds, Saturn becomes reachable on a practical timescale. If it fails, the longer chain outward may collapse. The precision required for this passage is difficult to overstate. Over hundreds of millions of miles, the spacecraft must arrive within a corridor narrow enough that the resulting bend in motion produces the needed departure path. The calculations must account for the positions and motions of Earth, Jupiter, and the spacecraft itself, as well as the small effects of earlier maneuvers and the long accumulation of tiny uncertainties. This is done with computing resources far more limited than those available decades later, which makes the achievement all the more impressive. Navigation at that scale is not a matter of overwhelming computational force. It is a matter of disciplined measurement, reliable models, and careful interpretation. Engineers and navigators receive radio tracking data from the spacecraft, compare the observed behavior with predicted motion, and refine their estimates continuously. The result is a kind of invisible piloting across deep space, conducted with mathematics, delayed signals, and a great deal of patience. Jupiter's gravity provides the energy transfer, but the spacecraft must still survive the approach and remain scientifically useful during it. As the probes close in, the giant planet grows from a bright target into a system, then into a world with its own weather, moons, radiation environment, and magnetic complexity. The timing of observations becomes critical because the encounter is brief relative to the years of travel that precede it. Instruments must be commanded carefully so that the period near closest approach yields the richest possible return. The tape recorders must capture data efficiently. The scan platforms must point with accuracy. The spacecraft body and antenna must maintain the stability needed for command reception and later transmission. Everything accelerates, not in the physical sense alone, but in operational tempo. A mission that has spent many quiet months in cruise suddenly enters a compressed period where every hour carries unusual scientific weight. Yet beneath this intensity, the larger mechanical role of Jupiter remains constant. The planet is both object of study and dynamic lever. It reshapes the trajectory of the spacecraft through its own motion around the Sun. This can be understood most clearly by imagining the encounter not from a fixed solar viewpoint, but from the moving frame of the planet itself. The spacecraft arrives relative to Jupiter, swings past, and departs relative to the Sun. However, it leaves with a new share of orbital energy taken from the enormous moving mass it has passed. Jupiter is so massive that this exchange makes no meaningful difference to the planet, but it makes an immense difference to the spacecraft. A mission that would otherwise need a larger launch vehicle, more fuel, or much more time is suddenly carried outward by the architecture of the solar system itself. The beauty of the maneuver is that it uses gravity not as an obstacle to be overcome, but as a resource. Human engineering yields part of the work to nature, provided that timing and placement are exact. This is one reason the 1977 alignment matters so much. Jupiter is not acting alone. The assist at Jupiter is valuable because it leads into later opportunities at Saturn, and for Voyager 2 beyond Saturn to Uranus and Neptune. The planets form a sequence in which each successful encounter makes the next one possible. Jupiter is the first and most essential handoff. Without it, the later outer system would remain much farther away in practical terms. The encounter therefore carries a double significance. It begins the first close exploration of the largest planet, and it enables the continuing outward reach of the mission. In quiet, mechanical language, Jupiter turns the Voyagers into deeper space missions than their launch vehicles alone could have made them. By the time each spacecraft departs the Jovian system, it does not merely leave with images and measurements, it leaves with a new future. The spacecraft have fallen toward Jupiter, but what the fall truly provides is escape toward the next immense dark, an increase in speed purchased through exactness, and the preservation of a path that continues outward along the rare chain first opened by the alignment of the giant planets. Jupiter does not resemble a larger version of Earth, or even a larger version of any ordinary planet in the inner solar system. It is a world of depth rather than surface, of atmosphere rather than ground, of scale so vast that familiar categories begin to fail. Seen from far away through a small telescope, it presents itself as a striped sphere with a great red mark and a set of bright moons. Seen up close by Voyager, it becomes something more violent, more dynamic, and more structurally rich than earlier models had prepared scientists to expect. The cloud tops alone reveal motion on a planetary scale. Broad bands circle the planet in alternating tones, but these are not static markings. They are the visible expression of powerful jet streams moving in opposite directions, with boundaries where winds race at immense speed. Storm systems form, interact, distort, merge, and tear apart across distances that on Earth would span continents. The famous Great Red Spot, known from telescopic observation for centuries, proves to be not a simple stain or stable feature, but a giant anticyclonic storm of exceptional complexity. It rises above the neighbouring cloud layers and rotates with a persistence that had already lasted longer than recorded modern history. Voyager images show smaller storms being drawn into its region, sheared apart and absorbed into the wider atmospheric pattern. This is weather on a scale that makes Earth's largest hurricanes appear local and brief. Yet the violence of Jupiter is not expressed by clouds alone. The entire planet radiates the fact that it is still active from within. One of Voyager's important findings is the confirmation, in increasingly detailed form, that Jupiter emits more energy than it receives from the distant Sun. This means that the planet is not merely warmed from outside, it still releases internal heat, likely left over in part from its formation and maintained by slow gravitational contraction. That internal energy drives atmospheric motion and helps explain why the cloud system is so energetic despite the planet's great distance from the Sun. Jupiter is often called a failed star because it formed from the same broad cosmic ingredients as stars, mainly hydrogen and helium, but never acquired enough mass to ignite sustained nuclear fusion in its core. The phrase can be misleading if taken too literally, yet it captures an important truth. Jupiter sits near the boundary between planet and something more stellar in composition and behaviour. It is not massive enough to shine by fusion, but it is massive enough to remain physically restless on a scale unmatched by any other planet in the solar system. Voyager's observations make this restlessness visible. The cloud decks are arranged in layers of different composition and temperature, and the colour differences across the planet hint at chemistry interacting with sunlight, heat, and motion. Ammonia, ammonium hydrosulfide, water, and other compounds likely contribute to the layered atmospheric structure, though the precise details are not all directly visible from the flyby alone. What is unmistakable is that Jupiter's atmosphere is deep, active, and driven by forces far beyond what had once been inferred from distant observation. Another revelation comes from lightning. Before Voyager, lightning is understood on Earth as a familiar product of storm physics, and scientists have reason to suspect that similar processes might occur elsewhere, but direct evidence remains limited. Voyager changes this by detecting radio signals and visible flashes associated with lightning in Jupiter's atmosphere. The flashes are seen on the night side, illuminating cloud tops from below. The radio instruments detect whistlers, characteristic signals produced by electromagnetic waves travelling along magnetic field lines after lightning discharge. These findings matter because they demonstrate that atmospheric electricity is not peculiar to Earth. The underlying process of charge separation and discharge can operate in very different planetary environments, including one with pressure, composition, and scale far removed from the terrestrial case. Jupiter's lightning is not only present, it appears immense, embedded deep in an atmosphere where the pressures and temperatures would overwhelm any familiar Earth weather system. This helps establish a broader comparative science of atmospheres, showing that the physical logic of storms extends across worlds even as its expression varies from place to place. Yet the atmosphere, for all its grandeur, is only one layer of Jupiter's violence. Surrounding the planet is a magnetic environment so powerful that it becomes one of the defining features of the entire Jovian system. Voyager reveals that Jupiter's magnetic field is stronger and more extensive than most prior models had suggested. This field traps charged particles and creates enormous radiation belts. These belts are fed in part by the solar wind and in part by material from the planet's own moons, especially from volcanic activity on Io, though the full importance of that connection becomes clearer through later analysis. For the spacecraft themselves, the radiation environment is not an abstract finding, it is a direct hazard. High-energy particles strike electronics, cause glitches, flip memory bits, and interfere with instrument performance. During the close approach, there are periods when engineers on Earth must watch carefully for signs that the bombardment may have caused permanent damage. The spacecraft survive, but not because Jupiter is gentle. They survive because of shielding, conservative engineering, and a measure of luck. The radiation belts around Jupiter are so intense that an unprotected human passing through the worst regions would receive a fatal dose in a very short time. In that sense, the giant planet is surrounded by an invisible killing field. Its beauty in telescopic images conceals a machine of charged particles and magnetic force extending millions of miles into space. The magnetic field also shapes auroral activity near the poles and interacts with the broader environment of the Jovian system in ways that reveal Jupiter less as an isolated planet than as the centre of a vast electromagnetic domain. The scale of that domain is itself astonishing. Jupiter's magnetosphere extends so far into space that it becomes one of the largest structures in the solar system, second only to the much larger heliosphere of the Sun. Voyager's measurements show that the region around Jupiter is not simply empty space between moons and planet. It is a dynamic medium filled with plasma, currents, particles, and field lines in motion. This makes Jupiter not just a planet with weather. but a system with its own space environment, a local cosmos organized by mass, rotation, heat, and magnetism. The more closely Voyager examines it, the more inadequate the old image of Jupiter as merely a large striped globe becomes. It is a place where storm, electricity, chemistry, gravity, and radiation all operate together on scales that are both planetary and system-wide. By the end of the flyby, one conclusion becomes unavoidable. Jupiter is not simply larger than Earth, it is different in kind. It shows that the giant planets are not reduced versions of the inner worlds. They are realms governed by deeper atmospheres, stronger fields, harsher radiation, and internal energies that create forms of activity far more expansive than earlier science had fully imagined. Voyager does not just improve the picture of Jupiter, it replaces it with something larger, harsher, and far stranger. Among Jupiter's large moons, Io proves to be the place where expectation breaks most abruptly. Before Voyager, moons are often imagined through the model provided by Earth's own moon and by the heavily cratered worlds known elsewhere in the inner solar system. They are thought of as old, cold bodies whose major stories belong to the distant past. Their surfaces bear the marks of ancient impacts, and their interiors are assumed to have cooled long ago into comparative stillness. This framework is not unreasonable given the evidence available at the time, yet it rests on a hidden generalization that Voyager is about to destroy. Io, seen from afar, is simply one of the 4 large Galilean moons discovered centuries earlier, seen up close. It becomes the first world beyond Earth where active volcanism is directly observed. The discovery is so consequential because it overturns not one detail, but an entire habit of thought. A moon can be geologically alive. A body far from the Sun can possess enough internal energy to reshape its surface continuously. A small world can influence the environment of a giant planet around which it orbits. These realizations begin with images and with the careful attention of people on Earth who understand that close inspection sometimes reveals what theory failed to expect. During the Jupiter encounter, a bright plume is identified rising from the edge of Io. At first the feature appears puzzling, possibly an imaging artifact or an unrelated object. Further analysis shows that it is an eruption, material launched hundreds of kilometers above the surface. Additional plumes and unusual surface forms soon make the conclusion unavoidable. Io is volcanic on a scale beyond anything then known elsewhere outside Earth. This is not a matter of a few isolated vents, it is a planetary condition. The surface is marked by sulfur-rich deposits, calderas, lava flows, and broad regions with very few impact craters. The lack of craters is itself a message. On an old inactive surface, impacts accumulate over immense spans of time. On Io they are erased because resurfacing is frequent. The moon is geologically renewed again and again, burying old scars beneath fresh material. The colours seen by Voyager reinforce the strangeness of the place. Yellow, orange, red, black, and white regions suggest sulfur compounds and a landscape dominated not by water ice or silicate desert in the familiar sense, but by volcanic chemistry operating under alien conditions. The question then becomes not whether Io is active, but how such activity is powered. The answer is one of the most elegant examples of gravitational interaction in planetary science. Io does not generate its heat mainly from radioactive decay in the way small rocky worlds may do over long periods. Its heat comes largely from tidal forces. Jupiter's gravity is immense, and Io orbits very close to the planet. If Io moved on a perfectly circular orbit and if no other moons perturbed it, the tidal flexing would eventually settle into a relatively stable pattern with less ongoing heating. But Io does not orbit in such calm isolation. The gravitational influence of Europa and Ganymede maintains a slight orbital eccentricity, preventing Io from becoming perfectly circular in its path. As a result, the pull from Jupiter changes across the orbit enough to knead the Moon continuously. Io is stretched and compressed, raised and released, deformed and relaxed in a relentless cycle. This repeated flexing generates internal friction and therefore heat. The process is called tidal heating. In Io's case, it is so strong that much of the Moon's interior remains partially molten or otherwise thermally active at depth, feeding extraordinary volcanism at the surface. The concept is simple in outline, but its implications are profound. Energy does not need to come only from sunlight or from internal radioactive sources. It can come from gravity acting through orbital resonance and mechanical deformation. Io becomes the most dramatic known example of this principle. Once recognized, tidal heating becomes a key to understanding other worlds as well, especially icy moons that show signs of subsurface oceans or youthful surfaces. On Io, the process is expressed in its hottest and most violent form. Surface temperatures near active eruptions can become extreme by planetary standards. Lava composition remains complex and not identical in every eruption, but the overall picture is clear. Io is not a dormant satellite. It is a body with persistent internal activity driven by the architecture of the Jovian system itself. In this sense, Io cannot be understood as an isolated moon. It is part of a gravitational arrangement in which Jupiter supplies the dominant pull and neighbouring large moons help sustain the orbital conditions that keep the heat engine running. The result reaches beyond geology. Material ejected from Io does not simply fall back and stay local. Volcanic gases, including sulfur and oxygen-bearing species, are released into space and become ionized. Once ionized, they are captured by Jupiter's magnetic environment and spread into a donut-shaped ring of plasma along Io's orbit, known as the Io plasma torus. This torus becomes a major source of particles for the Jovian magnetosphere. Electrical currents connect Io and Jupiter along magnetic field lines. Auroral footprints appear in Jupiter's upper atmosphere where these currents interact with the planet. A moon only slightly larger than Earth's own moon thus helps shape the electromagnetic weather of the largest planet in the solar system. That relationship is astonishing because it reveals a level of system-wide coupling that earlier simplified models had not prepared scientists to see. Io is not just heated by Jupiter. It feeds Jupiter's magnetosphere with material. Jupiter in turn acts on Io with overwhelming force. Their interaction is reciprocal, unequal in power but deeply linked in consequence. The scientific effect of this discovery is immediate and lasting. Old assumptions about moons as passive companions become difficult to maintain. If Io can be so active, then other moons may also contain hidden energy sources, buried oceans, internal differentiation, and complex histories. The outer solar system begins to look less like a set of frozen leftovers and more like a place of ongoing processes. This change in perspective matters as much as the discovery itself. Voyager does not merely add one more interesting object to a catalogue. It reveals that the catalogue has been organised around mistaken expectations. Io teaches that distance from the Sun does not guarantee geological quiet. It teaches that small worlds can be remade from within. It teaches that orbital relationships can generate heat, chemistry, and electromagnetic consequences on a system-wide scale. Above all, it teaches caution in the face of apparent familiarity. A moon seen for centuries as a bright point beside Jupiter turns out, under closer view, to be a world of eruption and renewal, one of the most restless places in the solar system, kept alive by gravity itself. Europa appears at first as a quieter world than Io, and in one obvious sense it is. There are no towering volcanic plumes rising visibly into space, no sulfur-rich colours announcing fresh eruption, no immediate spectacle of exposed internal fire. Yet the quiet surface that Voyager sees proves just as disruptive to earlier assumptions, because it suggests a different kind of hidden activity, one not expressed through heat and lava at the surface, but through ice, motion, and the possibility of liquid water sealed below. The moon is bright, smooth, and marked by dark lines that crisscross the surface in long arcs and intersecting bands. Compared with heavily cratered bodies elsewhere in the solar system, Europa looks unexpectedly young. This youth is not measured by a direct clock, but inferred from the scarcity of impact craters. On old inactive worlds, crater density accumulates over immense spans of time. On Europa, that record appears to have been erased or covered repeatedly. Something has renewed the surface. The question is, what kind of process can do that on a moon so far from the Sun? Voyager's images do not answer everything, but they establish the essential puzzle. Europa is an icy world, yet not a simple frozen relic. Its surface resembles a shell that has cracked, shifted, and perhaps opened and closed again. The long dark lineaments are not random decorations. They look like fractures in a global crust, places where stress has broken the ice and allowed darker material to appear or rise from below. In some areas, the surface seems to preserve broken plates that may have moved relative to one another and then been refrozen into place. The comparison with pack ice on polar seas is tempting, though Europa's setting is much colder, more rigid, and influenced by entirely different scales of force. What matters scientifically is that the patterns imply motion in the ice. A crust that moves and breaks in this way is difficult to explain if the entire body is solid to great depth. The simplest broad interpretation is that a layer of liquid or soft warm material exists beneath the outer shell, allowing the surface ice to deform, crack, and slowly rearrange over time. Once again, tidal heating becomes central. Europa orbits Jupiter farther out than Io does, so the tidal forces are weaker, but they are not absent. The Moon also participates in orbital relationships with neighbouring moons that help maintain a slight eccentricity in its path. This prevents the tidal flexing from disappearing entirely. The amount of heat generated is much less than on Io, yet on a world made largely of water ice, even a gentler supply of internal energy can have far-reaching consequences. It may not melt rock and drive open volcanism, but it may be sufficient to maintain an ocean beneath the frozen crust. Such an ocean would be concealed under ice perhaps many kilometers thick. Voyager cannot measure its full depth directly. But the logic opened by the flyby is powerful. If Europa contains a global subsurface ocean, then it may hold more liquid water than all the oceans on Earth combined. This is one of the most striking changes in scientific perspective produced by the mission. Before such discoveries, the search for potentially habitable environments beyond Earth tends to focus strongly on planets in the right distance range from their stars, where surface water could remain liquid. Europa suggests a different model. A world can be cold at the surface, far from the Sun, and still contain a long-lived internal ocean if tidal energy and insulation work together. In such a case, habitability no longer depends only on surface climate and direct sunlight. It can depend on internal heat, chemistry, and a hidden interface between water and rock far below an icy shell. This possibility matters because on Earth, wherever liquid water, chemical nutrients, and usable energy exist together, life appears remarkably persistent. Sunlight supports much of Earth's biosphere, but it is not the only possible energy source for living systems. At hydrothermal vents on the ocean floor, organisms thrive in complete darkness, supported by chemical disequilibrium produced where heated water meets mineral-rich rock. Europa raises the question of whether something broadly analogous could exist in a buried ocean, isolated from the surface, never touched by daylight, but supplied with energy through tides and geochemical interactions at the seabed. Voyager does not discover life and does not directly observe hydrothermal vents, yet it creates the scientific path by which such questions become serious rather than fanciful. The surface itself offers clues about the shell above this hidden ocean. The dark streaks may contain salts, irradiated compounds, or material brought upward through cracks. Jupiter's radiation environment bombards Europa's outermost surface, altering chemistry and producing substances that later observations and missions would study in far greater detail. The Moon therefore exists at a boundary between shielding and exposure. Beneath the ice, a potential ocean could be protected from radiation by a thick frozen roof. At the surface, the same Moon is embedded in Jupiter's harsh magnetic environment. This contrast gives Europa a layered character. The outer skin is cold, fractured, and irradiated. The deeper interior may be wet, dark, and comparatively stable over geologic time. The tension between those layers makes Europa one of the most scientifically compelling worlds in the solar system. Its importance continues to grow long after Voyager, because later missions and observations strengthen the case first opened by the flyby. The Galileo spacecraft provides additional evidence consistent with a conductive salty ocean beneath the surface, inferred from magnetic interactions. Space telescopes detect signs that may indicate material venting from the Moon. New missions are planned and launched to study its chemistry, ice thickness, internal structure, and possible exchange between ocean and surface. Yet the origin of this long scientific arc remains the moment when Voyager's cameras reveal that Europa is not cratered and inert as expected. That first shock of visual evidence is enough to redirect decades of planetary science. The Moon becomes a place where biology, geology, chemistry, and planetary physics intersect. In the outer solar system, where earlier imagination often pictured only frozen silence, Europa introduces the possibility of a habitable ocean world concealed beneath ice. It does so not through spectacle, but through restraint. The smoothness of the surface, the pattern of its fractures, and the absence of old scars all suggest that something below remains active. Europa's strangeness is therefore of a quiet kind. It is a moon that hints rather than announces. Its surface does not display the interior directly. It preserves signs that the interior exists, moves, and may still be warm enough for liquid water. In scientific history, this is enough. The quiet world becomes one of the most significant destinations of future exploration, because Voyager shows that stillness on the outside can hide an entirely different environment below. Before Voyager, rings belong in the popular imagination almost entirely to Saturn. The planet's broad, bright bands have been visible through telescopes for centuries, and they seem so singular, so visually defining, that they encourage the idea that rings are a rare embellishment added to one unusual world. Jupiter is known for clouds and storms. Uranus is known mainly as a distant pale planet. Neptune is farther still, dim and difficult. Saturn alone appears crowned. This perception begins to change when Voyager reaches Jupiter and detects a faint ring system where none had been seen before. The discovery is modest in appearance compared with Saturn's brilliance. Jupiter's rings are dark, thin, and composed largely of dust, easy to miss without the right geometry and instrumentation. Yet the scientific implication is much larger than the visual spectacle. If Jupiter has rings, then rings may not be exceptional at all. They may be a common product of giant planets, formed and maintained by processes that operate across multiple systems. What had seemed unique may instead be one expression of a broader rule. This shift in understanding becomes one of Voyager's lasting contributions because it transforms rings from a decorative anomaly into a category of planetary structure requiring general explanation. The existence of a ring system means that a planet is not only orbited by moons of substantial size, but also by enormous populations of smaller particles whose behavior is governed by gravity, collisions, radiation forces, and interactions with nearby satellites. Rings are therefore not static ornaments. They are dynamic systems. Jupiter's faint rings suggest that even where ring material is sparse and dark, the underlying processes can still operate. Later observations at Uranus and Neptune reinforce this view. Uranus is found to possess narrow dark rings that had first been inferred from stellar occultation and are then placed in clearer context by close exploration. Neptune too is shown to have rings, including incomplete arcs that appear confined rather than spread uniformly around the planet. By the end of the Voyager era at the giant planets, all 4 outer giants are known to possess ring systems. The question is no longer whether rings are rare. The question becomes why the same broad class of structure can look so different from one planetary system to another. Saturn's rings are bright and icy, made largely of water ice particles that reflect sunlight efficiently and produce the visual magnificence long visible from Earth. Jupiter's rings are thin, dusty, and much darker. Uranus presents narrow, sharply defined bands. Neptune includes arcs that should, in a simple, ordinary picture, smear out with time but somehow persist. These differences force scientists to move beyond the idea of rings as a single phenomenon with minor local variation. Each ring system must be understood through its source material, particle size distribution, interactions with moons, and relation to the planet's gravity and environment. Voyager's role here is not merely to add more examples. It reveals that ring physics is subtle. The particles in a ring do not simply circle forever in perfect calm. They collide, exchange momentum, clump, disperse, and respond to resonances created by nearby moons. Small moons can confine rings, open gaps, or excite waves. Dust can be replenished by impacts on tiny satellites. Radiation pressure and electromagnetic effects may matter for the smallest particles. What from a distance looks like a simple, smooth band often proves on closer inspection to be a structured region full of edges, gradients, braids, waves, and local disturbances. Rings therefore become laboratories for orbital dynamics, places where invisible forces become visible through pattern. In that sense, they are among the clearest demonstrations that the outer solar system is not an arrangement of isolated objects drifting in emptiness. It is an interconnected environment in which particles, moons, and planets continually shape one another. Voyager also changes the emotional meaning of rings in planetary science. Before close exploration, rings can easily be treated as visual curiosities, dramatic but secondary to the planets they surround. After Voyager, they become central subjects in their own right. They preserve information about impact processes, moon disruption, tidal limits, and the long evolution of planetary systems. Some ring material may be ancient, left over from early phases of solar system history. Some may be relatively young, produced by broken moons or by repeated collisions. The age of ring systems becomes a serious scientific question because ring particles are not necessarily permanent. Collisions can grind them down. Planetary atmospheres and magnetic fields can draw material away. Moons can scatter particles inward or outward. A ring seen today is therefore not guaranteed to be a primordial feature unchanged since formation. It may be temporary on geological timescales, maintained only by continuing sources and delicate balances. This dynamic perspective owes much to Voyager because direct observation of multiple ring systems makes such questions unavoidable. The outer giants no longer appear as simple spheres separated by large distances. Each is embedded in a local architecture of moons, dust, and debris. Rings reveal where gravity sorts matter into flattened structures, where resonances create order, and where instability leaves signatures in shape and brightness. The same gravitational laws apply across all the giant planets, yet each system expresses those laws through different histories and materials. Saturn's brilliance no longer stands alone. It becomes one member of a family of ring worlds, though still the most visually spectacular. This broader view also has implications for understanding planetary formation beyond the solar system. Rings show that fine-scale structure can emerge naturally around large bodies when enough particulate material is present and when tidal and orbital conditions are right. They hint at the processes by which moons may grow, migrate, or be destroyed. They illustrate how disks of matter behave under gravity, a theme that extends outward to protoplanetary disks around young stars and inward to accretion environments around compact objects, though those are physically distinct regimes. Within the solar system, however, rings remain the most accessible and immediate expression of this wider principle. Voyager does not solve every question about them, but it makes clear that they are not decorative leftovers. They are active systems with histories. By the time the spacecraft have completed their giant planet encounters, the old idea of Saturn as the sole ringed exception is gone. In its place stands a new understanding. Rings are common among the giant planets, but common does not mean simple. Each system is different. Each one records a balance between creation and erosion, confinement and spreading, invisibility and brilliance. The beauty that once seemed singular now appears as a family of related phenomena, and the outer solar system becomes richer precisely because repetition does not produce sameness. It produces variation structured by the same laws but shaped by different outcomes. When Voyager reaches Saturn, the planet first appears to confirm an image already familiar to human culture. Here is the ringed world, pale and immense, encircled by bands that have defined it in drawings, telescopes, and imagination for centuries. Yet as with Jupiter, closeness does not simply sharpen an old picture. It breaks it apart and replaces it with something more intricate. Saturn's rings had long been described in broad divisions, as if a few major bands and gaps could account for the visible structure. Voyager reveals that this apparent simplicity is an illusion of distance. The rings are not a handful of clean separate zones. They are composed of countless ringlets, narrow strands of material packed into a system so detailed that every increase in resolution uncovers still more complexity. What had seemed like broad, continuous sheets resolve into layered structure, with brightness changes, fine divisions, twisted forms, and local disturbances that no telescope on Earth had been able to show in full. The effect on science is immediate. Saturn's rings are no longer merely an emblem of order and symmetry. They become one of the most elaborate dynamical systems in the solar system, a place where gravity, collisions, and orbital resonance produce patterns of extraordinary delicacy. The ring particles themselves are mostly water ice, ranging in size from tiny grains to much larger chunks, all circling Saturn in flattened orbital motion. Yet this flattening does not imply stillness. The rings are busy at every scale. Particles collide constantly, exchanging momentum and gradually redistributing energy. Some regions appear denser than others. Some are structured by resonances with moons that orbit outside or within the ring system. In these resonances, the repeated gravitational pull of a moon acts on particles at specific orbital locations, clearing gaps, sharpening edges, or driving wave-like patterns through the material. The Great Cassini division, visible from Earth, is one familiar expression of this logic, but Voyager shows that the same basic principle extends far beyond the textbook picture. The ring system is full of smaller divisions and organized disturbances, evidence that it is being shaped continuously by nearby bodies and by the internal behavior of the ring particles themselves. One of the most striking discoveries is the role of shepherd moons, small satellites whose gravity helps confine narrow rings. In the F ring, for example, tiny moons, later named Prometheus and Pandora, orbit on either side, influencing the ring material and helping maintain its narrow structure. This idea of shepherding is important because it reveals that moons need not be large to shape planetary systems in significant ways. Even small objects can act as gravitational guides, containing ring particles and sculpting local form. The image of Saturn's rings therefore changes from that of a passive disk to that of a responsive environment held in pattern by a network of interactions. Voyager also detects braided structures and strange irregularities in the F ring, features that suggest the ring is not a quiet boundary, but a place of ongoing perturbation. The neat appearance seen from afar gives way to evidence of continual disturbance, confinement, and reorganization. Another surprise comes in the form of spokes, dark radial features seen across parts of the B-ring that seem to cut across the ordinary circular arrangement. These spokes are puzzling because ring particles orbit Saturn according to Keplerian motion, where inner particles move faster than outer ones. A stable radial line should shear apart quickly under such conditions. Yet the spokes appear and vanish on timescales, suggesting that something more than simple orbital motion is involved. The leading explanation points toward electromagnetic effects acting on fine dust grains, linking the spokes to Saturn's magnetic environment and to charging processes within the rings. Voyager does not solve the phenomenon completely, but it establishes that the rings are influenced not only by gravity and collision, but also by electrical processes under the right conditions. This widens the scientific frame again. The ring system is not merely a mechanical disk, it is part of Saturn's wider environment, responsive to forces that extend beyond ordinary particle crowding. The spacecraft's passage near the ring plane provides another lesson, one more physical than visual. Instruments record frequent impacts from tiny particles, showing that even regions that appear serene from afar are in fact full of fast-moving debris. Saturn's rings are beautiful because sunlight reflects from innumerable icy particles in orderly orbit, but that order exists alongside ceaseless collision at the particle level. The spacecraft survives the crossing, yet the encounter reminds mission teams that the ring system is not a decorative image pasted around a planet. It is matter in motion, and matter in motion at orbital speed can be dangerous. This realization adds weight to the broader scientific picture. Rings are not symbolic adornments. They are real particulate environments with mass, structure, and physical risk. The moons around Saturn deepen the sense that this is a system of unusual variety. Mimas, though small, help shape ring structure through resonance. Enceladus appears unexpectedly smooth and youthful in places, suggesting internal activity not yet understood in Voyager's time. Hyperion tumbles chaotically, showing that not all moons rotate in simple, stable ways. Iapetus presents a startling contrast between bright and dark hemispheres, preserving an unsolved puzzle in visible form. Saturn is thus not only a planet with complex rings, it is the centre of a miniature planetary system where each moon seems to tell a different story. Yet within this diversity, the rings remain the defining field of interaction. They respond to moons, they record resonances, they display local confinement, and they reveal the behaviour of particulate matter under gravity with unusual clarity. By the end of Voyager's Saturn encounter, the long-standing cultural image of the ringed planet remains, but its meaning has changed completely. The rings are still beautiful, but their beauty now rests in complexity rather than simplicity. They are not broad, stable bands surrounding a planet in silent perfection. They are layered, crowded, dynamic structures shaped by tiny impacts, repeated gravitational nudges, local confinement, and unexpected electromagnetic effects. Saturn itself becomes more than a single iconic globe. It becomes a system of extraordinary fine structure, where every closer look reveals another level of order emerging from motion. Titan remains hidden when Voyager arrives. This fact gives the Moon a very different character from the other worlds encountered so far. Jupiter's storms are visible. Io's eruptions announce themselves. Europa's fractures can be traced across the ice. Saturn's rings reveal their structure under close inspection. Titan does not do this. Its surface stays concealed behind a thick global haze that blocks ordinary imaging and turns the Moon into a softly bounded orange sphere. Even at close range, there is no direct view of mountains, plains, rivers, or craters. Yet this concealment is not a failure of the encounter. It is the scientific message itself. Titan is a world wrapped in air dense enough to hide the ground. That alone makes it extraordinary, because among moons in the solar system, such a substantial atmosphere is rare. Titan is larger than the planet Mercury, and Voyager's instruments show that its atmosphere is composed mainly of nitrogen, the same gas that dominates Earth's atmosphere. This similarity matters, but so do the differences. Mixed into Titan's nitrogen are methane and other hydrocarbons, and the conditions of temperature and pressure are so cold that methane can play a role broadly analogous to the role water plays on Earth. This does not make Titan Earth-like in any simple sense. The chemistry, sunlight level, temperature, and surface state are profoundly different. But it does mean that Titan may support a weather cycle involving evaporation, condensation, clouds, and rain, not of water, but of methane and ethane. In that realization, Voyager opens one of the most remarkable environmental possibilities in the outer solar system. The atmosphere itself is thick and active enough to shape the surface below, even though the surface cannot yet be seen. Measurements indicate that the pressure at Titan's surface is greater than Earth's surface pressure at sea level. The haze consists of complex organic particles created when sunlight and energetic particles act on methane and nitrogen in the upper atmosphere, driving photochemistry that builds larger molecules and suspended aerosols. These particles scatter light efficiently, especially at visible wavelengths, which is why Titan appears shrouded and why ordinary cameras cannot see through to the ground. The atmosphere therefore does more than exist. It transforms incoming energy and creates a chemical factory above the hidden surface. In the upper layers, methane is broken apart and rebuilt into more complex compounds. Some of these eventually drift downward, settling toward the lower atmosphere and the ground in a slow organic rain. The result is a moon where air and chemistry are deeply entangled. Titan becomes a natural laboratory for studying carbon-rich chemistry under conditions unlike those of Earth, but still relevant to understanding planetary atmospheres and prebiotic processes. Because the surface temperature is so low, around -290 degrees Fahrenheit, water ice there behaves less like soft snow and more like rock. Methane and ethane, by contrast, can exist as gases and liquids under Titan's conditions. This reverses many familiar expectations. On Earth, water shapes rivers, lakes, seas, and clouds, while methane is a trace gas. On Titan, methane may carve channels, fill basins, and fall from the sky, while water remains locked into a frozen structural role. Voyager cannot confirm all these surface processes directly, yet the atmospheric data make them scientifically plausible enough to transform Titan from a vague curiosity into a major target for future exploration. A moon with a thick nitrogen atmosphere and possible methane weather is not simply another icy satellite. It is a whole environmental system, one in which climate, surface evolution, and organic chemistry may interact over immense spans of time. The haze also creates an important scientific frustration, and frustration of this kind can be productive. The inability to see the surface means that Titan immediately generates unanswered questions of unusual power. What landscapes lie below? Are there liquid reservoirs? Is the surface ancient and cratered, or young and reshaped? Do winds move particles across broad plains? Does methane rain carve valleys and feed lakes or seas? Voyager cannot answer these questions, but by making them unavoidable, it defines the agenda for later missions. The moon becomes a place that future exploration must return to with radar, infrared instruments, and eventually atmospheric descent. In that sense, Titan's hiddenness is not a closed door. It is an invitation structured by ignorance. The most important discovery is that ignorance now has a clear object. Scientists know enough to understand that Titan is not simple, and not enough to see why. This combination is often where major planetary science begins. Titan also matters because it broadens the meaning of habitability and environmental diversity in the solar system. It is far too cold for liquid water to stand openly at the surface, and no one mistakes it for a straightforward abode of life in Earth's present form. Yet it demonstrates that atmospheres and surface cycles can exist in radically different chemical regimes. Worlds do not need to imitate Earth closely in order to possess climate, weather, and active exchange between air and ground. Titan's methane cycle suggests that planetary processes we associate with one substance may be transferable, in altered form, to another. This enlarges the comparative study of planets and moons. It teaches that similar physical patterns can emerge from different materials if pressure and temperature allow. That lesson will later extend well beyond Titan, influencing the way scientists think about exoplanets, atmospheric chemistry, and the range of stable environments possible across the universe. Titan also preserves a possible connection to early Earth, though this comparison must be handled carefully. The Moon's atmosphere, rich in nitrogen and organic chemistry, offers a setting in which complex carbon compounds can form without life. It is not a recreation of young Earth, because the temperatures and available liquids are different, but it can still illuminate how organic molecules arise in planetary atmospheres before biology enters the story. For this reason, Titan becomes valuable not only as a strange distant moon, but as a natural experiment in chemical evolution. Voyager does not solve the experiment, but it identifies it clearly. The choice to send Voyager 1 close to Titan has major consequences for the larger mission. The trajectory needed for this scientifically valuable flyby directs the spacecraft out of the plane in which the other giant planets orbit, which means Voyager 1 will not continue onward to Uranus and Neptune. This makes Titan not just a subject of study, but a branching point in mission history. Saturn is the final major planetary encounter for Voyager 1, because Titan is judged important enough to justify that path. The decision itself reveals how significant the Moon appears even through haze. A hidden world with a dense atmosphere is worth sacrificing a later chain of planetary opportunities. By the end of the encounter, Titan remains visually mysterious, but scientifically it has become one of the most compelling bodies in the outer solar system. Its atmosphere is real, thick, chemically rich, and climatically suggestive. Its surface is unseen, yet already active in the imagination of science because the air above it implies processes below. Voyager leaves Titan partly unexplained, but it leaves behind something equally powerful certainty that beneath the orange veil lies a world unlike any then known. By the time Voyager 2 leaves Saturn, the mission has already exceeded the official horizon imagined at launch. What began as a reduced program centered on Jupiter and Saturn now continues outward into a region no spacecraft had ever explored directly. This extension is not automatic. It depends on the health of the spacecraft, the accuracy of earlier navigation, and the continued willingness of institutions on Earth to support a mission whose rewards lie years ahead and at distances so vast that ordinary intuition begins to fail. Yet the outward chain remains open, and Voyager 2 follows it. Uranus and Neptune are not merely farther versions of Jupiter and Saturn. They belong to a different subclass of giant planet, now often called ice giants because their internal composition includes larger fractions of water, ammonia, and methane-rich materials in comparison with the hydrogen and helium dominance of Jupiter and Saturn. Before Voyager, these worlds are known mainly through distant telescopic observation, their disks small, their atmospheres only partly characterized, their moons dim and few in number. The movement of Voyager 2 toward them therefore extends not just the mission's range, but the taxonomy of planets. The solar system does not end with a repetition of familiar giants. It opens into planets whose structure, colour, magnetic behaviour, and satellite systems add new kinds of difference. Uranus is the first encounter, reached in 1986. Even before the details of its moons and rings are considered, the planet itself forces a revision of expectation. It rotates in an extreme axial tilt, essentially rolling around the Sun on its side. This unusual geometry means that its seasons are unlike those of any other planet, with poles and equatorial regions experiencing sunlight in patterns that challenge simpler assumptions about atmospheric circulation and long-term climate. Voyager finds a world that appears visually subdued compared with Jupiter and Saturn, its atmosphere relatively bland at first glance, blue-green in colour because methane absorbs red light. Yet beneath that calm appearance lies strangeness of a more structural kind. Uranus possesses a magnetic field that is both tilted sharply relative to the planet's rotation axis and offset from the planet's centre. This is not a minor detail. It means the magnetosphere has a geometry unlike the more centred dipole fields familiar from Earth or roughly aligned giant planet cases. As Uranus rotates, its magnetic environment wobbles through space in a highly unusual way, producing a magnetospheric structure that is complex, asymmetric, and instructive for comparative planetary physics. The lesson is again that planetary systems can differ not just in appearance, but in deep architecture. Uranus also confirms that rings are not limited to Saturn's bright display or Jupiter's faint dust bands. Its rings are narrow, dark, and sharply defined, showing that ring systems can exist in a much less reflective and more austere form. These rings had been detected before Voyager through the technique of stellar occultation, when starlight was seen blinking off as material passed in front of it, but the spacecraft encounter places them in direct planetary context. The moons add further richness. Several new moons are discovered, and the known moons reveal surfaces marked by tectonic features, impact history, and in some cases hints of geological evolution. Miranda becomes especially striking, with its bizarre patchwork terrain of cliffs, ridges, and differently textured provinces. Its appearance suggests a history that may involve partial disruption, reassembly, or intense internal deformation, though the exact sequence remains debated. Once again, a small moon refuses to behave like a simple inert remnant. The outer solar system continues to replace monotony with diversity. Then comes Neptune in 1989, the last planetary stop of the mission and the most distant planet in the solar system. If distance alone determined character, Neptune might have been expected to appear dormant, cold, and static. Voyager reveals the opposite. Despite receiving very little solar energy, Neptune shows strong atmospheric activity, including high-speed winds and major storm systems. The Great Dark Spot, observed during the flyby, demonstrates that the planet's atmosphere is dynamic and capable of sustaining large-scale weather. This finding echoes an earlier lesson from Jupiter, but in a different regime. Internal energy matters profoundly. Even in the deep outer solar system, far from intense sunlight, giant planets can remain meteorologically active if they possess internal heat and atmospheric conditions able to organize motion. Neptune's blue color, also linked to methane absorption, does not signify stillness. It marks a world of fast winds and layered clouds. Neptune's magnetic field, like that of Uranus, is significantly tilted and offset, reinforcing the sense that the ice giants form a distinctive class. Their interiors and dynamo regions do not generate magnetic fields in the same simple way as the larger gas giants or terrestrial planets. This becomes an important clue for models of planetary interior structure. The ring system at Neptune adds yet another variation. Rather than forming only uniform continuous bands, parts of the ring system include arcs, denser segments that appear confined in ways that should not persist for long under simple orbital spreading. Their existence suggests gravitational interactions, likely involving nearby moons, that preserve local concentration of material. Here again, the outer planets demonstrate that ring dynamics cannot be reduced to one visual template. Neptune also carries perhaps the most emotionally resonant moon of the late Voyager encounters, Triton. This large moon orbits Neptune in a retrograde direction, opposite to the planet's rotation, strongly implying that it was captured rather than formed in place. Its surface is cold, bright, and geologically surprising. Voyager observes dark plumes rising above the surface, likely driven by nitrogen sublimation and pressure beneath translucent surface layers. Triton is therefore active, though in a way very different from Io. Instead of tidal fire and sulfur volcanism, it shows a cold form of geyser like venting powered by seasonal sunlight and volatile ices. The surface is relatively young in places, marked by plains, ridges, and textures suggesting ongoing or recent renewal. Triton matters because it extends the lesson of active moons into yet another environment. Even near the outer edge of the planetary system, bodies can remain dynamic. Geological activity is not confined to warm worlds or to those close to the Sun. By the time Voyager 2 leaves Neptune behind, the outer solar system has ceased to be a sparse region of dim, remote planets. It has become a layered frontier full of different planetary classes, unusual magnetic fields, narrow rings, captured moons, active surfaces, and atmospheric behaviours no one could have described with confidence before direct encounter. The mission has also completed the transformation of the original reduced plan into something close in spirit to the grand tour once denied by budget. Not every path was taken by one spacecraft, and not every question was answered, but the giant planets have now been visited in sequence. Their differences are as important as their shared status. Together they reveal that the outer solar system is not the repetitive cold margin of the Sun's domain. It is a set of distinct worlds, each with its own structure, history, and local system, and Voyager has carried human observation across all of them, before heading onward into the dark beyond the last major planet. What Voyager changes is larger than the sum of its flybys. Each planetary encounter produces discoveries that matter on their own, but the deeper transformation comes from the way those discoveries alter the structure of scientific expectation. Before the mission, the outer solar system is often understood in broad and simplified terms. Jupiter and Saturn are giant planets with clouds and moons. Uranus and Neptune are distant cold worlds. Moons are assumed in many cases to be old and largely inactive. Rings are associated mainly with Saturn. The region beyond the asteroid belt appears remote not only in distance, but in conceptual richness. It is known, yet only thinly known. Voyager changes this by replacing a distant outline with direct encounter. The result is not simply more detail, it is a different map of reality. The giant planets cease to be generic categories and become distinct worlds with their own internal energies, magnetic structures, ring systems, atmospheric dynamics, and families of moons. Their satellites cease to be mere companions and become places in their own right, some volcanic, some icy, some hidden under atmospheres, some geologically active in ways no earlier theory had anticipated. The outer solar system no longer looks like a collection of cold leftovers, it looks like a domain of ongoing processes. This shift is one of Voyager's greatest scientific achievements because it changes not just what is known, but what kinds of questions become possible to ask. EO shows that tidal heating can sustain extreme volcanism far from the sun. Europa suggests that oceans may exist beneath ice, protected from radiation and warmed from below. Titan reveals that a moon can sustain a dense atmosphere and perhaps a full weather cycle based on methane rather than water. Saturn's rings become laboratories for orbital dynamics rather than simple visual wonders. Uranus and Neptune expand the planetary family, showing that giant planets come in more than one architectural form. Triton and other moons demonstrate that activity survives even in severe cold. The cumulative effect is a solar system more varied, more connected, and more dynamic than previous generations had imagined. Voyager's scientific importance also lies in method. The mission proves the value of comparative planetary science. It is no longer enough to study one planet and assume the rest are scaled variations. Similar physical laws operate across the solar system, but they produce sharply different outcomes depending on composition, distance, orbital history, internal heat, and interaction with nearby bodies, gravity, magnetism, chemistry, radiation, and fluid motion appear everywhere, yet nowhere in exactly the same arrangement. Voyager turns this into a practical scientific framework. By visiting multiple giant planets with instruments capable of measuring atmospheres, plasmas, magnetic fields, particles, and surfaces, the mission allows scientists to compare worlds directly rather than through isolated inference. The value of that comparison extends far beyond the specific data returned in the years of flyby. It shapes later missions, later theories, and later ways of organizing planetary knowledge. Entire generations of spacecraft follow paths partly defined by Voyager's questions. Galileo returns to Jupiter and its moons with more focused goals. Cassini enters Saturn orbit and studies Titan and Enceladus in sustained detail. New missions to Europa are developed because Voyager first made the moon scientifically irresistible. Even in the era of exoplanets, when planets around other stars are discovered in great numbers, Voyager's legacy remains active. The mission taught scientists how much variety planetary systems can hide behind simple categories. That lesson becomes crucial when interpreting distant worlds seen only as small signals in starlight. Yet Voyager is not only a scientific reordering, it is also a long demonstration of engineering continuity. The spacecraft outlive their original mission by decades, then outlive the planetary system they were built to explore in the narrow operational sense. Their cameras are turned off, many instruments fall silent, power declines, heaters are reduced, subsystems are sacrificed. Still, the probes continue. They do not remain important out of sentiment alone. They remain important because they enter a new scientific role at the boundary of the heliosphere and then beyond it. They become the first direct samplers of interstellar space. In doing so, they alter the meaning of mission extension. This is no longer merely an old spacecraft surviving beyond expectation. It is a machine whose continued survival opens an entirely new field of measurement. The same probe that once photographed Jupiter's clouds now measures plasma, cosmic rays, and magnetic conditions in the space between stars. There is a quiet grandeur in that continuity. A mission planned for a few years becomes a human presence stretched across nearly half a century, not because anyone at launch could guarantee it, but because the design was conservative, the operations were skillful, and the failures arrived slowly enough to be managed. In this way, Voyager changes the temporal imagination of exploration. It shows that a machine built in one political era can continue producing knowledge in another, and then another, carrying scientific intention across generational time. The people who approved the budget, the people who built the hardware, and the people who now interpret its last signals are not the same people. Yet the mission binds them together through continuity of purpose. Voyager also carries symbolic weight that is difficult to separate from its science, though the symbolism is strongest when grounded in the actual facts of the mission. These are two small machines made with limited memory, modest power, and a finite lifespan, moving farther than any human object has moved while still speaking to its makers. They carry the golden record, a statement of human self-description attached to an act of measurement. They travel without crew, without hope of return, and without expectation of arrival at any destination meaningful on human timescales. Their value lies in passage, observation, and persistence. In a universe where most distances are too large for comfort and most timescales too large for ordinary life, Voyager becomes a measured answer to those scales. It does not conquer them, it enters them. It shows that understanding can proceed by increments, by patience, by careful instruments, and by machines willing to keep going after the original story appears complete. When the final signals eventually cease, that meaning will remain. The spacecraft will continue outward in silence, carrying dead instruments, cooling structures, and a still legible record through the galaxy. Their active mission will end, but their historical role will not. They will remain the farthest material trace of a species that looked outward, built modestly, discovered more than it expected, and found that beyond the solar system there was not emptiness in the simple sense, but a larger context waiting to be measured.